Hello everyone. Today we are going to discuss about the Norton's theorem lab experiment theoretical calculations. Okay. So before going to the theoretical calculations, let's see what is the statement of the theorem. It states that in any linear bilateral complex network having more number of elements, the entire network can be replaced with an equivalent circuit called as a Norton's equivalent circuit, which is consist of Norton's equivalent current that is connected in parallel with the Norton's equivalent resistance. If you see the practical diagram of the Norton's equivalent circuit, this is the given Norton's theorem. This is the given circuit. For the given circuit, the total circuit can be replaced with an equivalent current source that is called as IN that is connected in parallel with the equivalent resistance RN. Okay, this is the equivalent circuit of the Norton's theorem. There is a procedure to find IN and there is a procedure to find RN. Initially, we will find out IL here. After finding the IL, we will find out IN. After finding the IN, we will find out RN. After finding the RN, finally, we will find out IL dash here. Assume that it is IL dash, the current passing through this load resistance. So, after calculating the equivalent circuit, we have to verify IL, that is current passing through this branch for the given circuit, that must be equal to the current passing through the same branch after calculating the equivalent circuit. This we have to verify theoretically. IL should be equal to IL dash, then we can say that Norton's theorem is verified. The first step is to find out IL. So before going to the IL, so let's see what are the parameters we have to find out theoretically. First we have to find out IL for the different voltages 15, 20, 25 volts. And after that we have to find out IN, and after that we have to find out IL dash. Okay, RN we will find out. RN also Norton's equivalent resistance. Let's see one by one the theoretical calculations of the Norton's theorem. First we will find out to find IL. First we will find IL, that is current passing through this load resistance. Okay, for the 15 volts, initially we have to apply 15 volts here. At 15 volts, what is the load current? That we have to find out by using the mesh analysis here. Assume that in this I1 current is flowing and assume that in this I2 current is flowing. Okay, if we apply KVL, apply KVL in loop 1. Yeah, if we apply KVL in loop 1, we will get 15 is equal to 1.8 I1 plus the common resistor is 1.8 into I1 minus I2. If we simplify this, we will get 3.6 into I1 minus 1.8 into I2. Assume that it is equation number 1. Now, apply KVL in loop 2. If we apply KVL in loop 2, we will get, as there is no source in the loop 2, 0 is equal to 1 into I2 plus 1.8 into I2 plus the common resistor, that is 1.8 into I2 minus I1. Okay. Now, if we simplify this, we will get minus 1.8 into I1 plus that is 4.6 into I2. I2 is equal to 0. This is equation number 2. Okay. From this, if we calculate equation number 1 and equation number 2, we will get I1 is equal to 5.18 milliamps and I2 we will get 2.02 milliamps. From 1 and 2, equation 1 and 2, we got I1 and I2 values. The current passing through this branch is I2. So from this we can say that load current IL is equal to I2 is equal to 2.02 milliamps for the 15 volts. Now let's see for the different voltages, that is 20 volts and the 25 volts. If we apply KVL in the loop 1 and loop 2, we will get, it is we are applying 20 volts here. Assume that in this I1 current is flowing, and assume that in this I2 current is flowing. This is the load current IL. If we apply KVL in loop 1, apply KVL in loop 1, if we apply KVL in loop 1, we will get 3.6 into I1 plus, sorry, it is minus, okay, 3.6 into I1 minus 1.8 into I2 is equal to 20. This is equation number 1. If we apply KVL in loop 2, if we apply KVL in loop 2, we will get minus 1.8 into I1 plus 4.6 into I2 is equal to 0. This is equation number 2. From equation number 1 and 2, we will get I1 is equal to 6.90 milliamps and I2, we will get I2 is equal to 2.70 milliamps we will get. Here, the current passing through this branch is I2. So, from this we can say that load current IL is equal to, that is I2, 2.70 milliamps. This is about the load current. For the given voltage, supply voltage is equal to 20 volts. Now let's take 25 volts. If we take the 25 volts, we will get the supply voltage is 25 volts. Here the current passing through the load resistance is assume IL. If we apply KVL here, assume that I1 current is flowing in the loop 1 and the I2 current is flowing in the loop 2. Here also same procedure, apply KVL in loop 1. If we apply KVL in loop 1, we will get 3.6 into I1 minus 1.8 into I2 is equal to 25. This is equation number 1. If we apply KVL in loop 2, we will get minus 1.8 into I1 plus 4.6 into I2 is equal to 0. This is equation number 2. From equation number 1 and 2, we will get I1 is equal to 8.63 milliamps and I2 is equal to 3.37 milliamps. Here the current passing through this branch is I2. So from this load current IL is equal to I2 only. That is 3.37 milliamps. Like this we will calculate. This is the procedure to find IL for the 15 volts, 20 volts and 25 volts. Now let's see how to find IN. Okay, to find IN, replace the total circuit with, here we will short circuit the load resistance and find the current passing through the short circuit terminal. This is nothing but IN. Okay, this is the given circuit, and for the given circuit to find out IN, the procedure is short circuit the load resistance and find the current passing through this load resistance. Here we are applying 15 volts. If we apply 15 volts here, we will get, assume that in this I1 current is flowing, and here also we are applying the mesh analysis. I2 current is flowing. Okay, apply KVL in loop 1. If we apply KVL in loop 1, we will get 15 is equal to 1.8 into I1 plus the common resistor is 1.8 into I1 minus I2. If you simplify this, we will get 3.6 into I1, 3.6 into I1 minus 1.8 into I2 is equal to 15. This is equation number 1. Now the same KVL if we apply in loop 2, we will get 0 is equal to 1.8 into I2 plus 1.8 into I2 minus I1. If we simplify this, we will get minus 1.8 into I1 plus 3.6 into I2 is equal to 0. This is equation number 2. From equation number 1 and 2, if we calculate I1 is equal to, we will get 5.55 milliamps, and I2 value we will get 2.77 milliamps. So as we know that the current passing through this branch is I2, so IN is equal to I2 is equal to 2.77 milliamps. For the supply voltage is 15 volts. Now let's say by taking the different voltages. Now here I am taking the supply voltage is 20 volts. For this I am applying I1 current in the loop 1, I2 current in the loop 2. Okay. If we apply KVL in loop 1, apply KVL in loop 1. If we apply KVL in loop 1, assume that the current passing through this branch, this is the Norton's current IN. Okay, if we apply KVL in loop 1, we will get 3.6 into I1, 3.6 into I1 minus 1.8 into I2 is equal to 20. This is equation number 1. If we apply KVL in loop 2, if we apply KVL, finally we will get minus 1.8 into I1 plus 3.6 into I2. This is equal to 0, equation number 2. From equation number 1 and 2, we will get I1 is equal to 7.40 milliamps and I2 is equal to 3.70 milliamps. As we know that the current passing through the low resistance, this branch is I2, that is IN. Sorry, it is IN. It is IN. IN is equal to I2 is equal to 3.70 milliamps. Okay. Now let's see it 25 volts. Okay. Now if we see the 15 volts calculation, this is 2.7 we got, and now if we see the 25 volts, I'm applying the supply volt. By taking the supply voltage, I'm applying the mesh analysis and finding the current passing through this branch, that is IN here. Okay, assume that in this I1 current is flowing and assume that in this I2 current is flowing. Here also same, apply KVL in loop 1. If we apply KVL in loop 1, we will get 3.6 into I1 minus 1.8 into I2 is equal to 25. This is equation number 1. If we apply KVL in loop 2, we will get minus 1.8 into I1 plus 3.6 into I2. This is 0. This is equation number 2. From equation number 1 and 2, we will get I1 is equal to 9.25 milliamps and I2 is equal to 4.62 milliamps. The current passing through this branch is I2. So from this we can say that IN is equal to I2 is equal to 4.62 milliamps. So like this we will calculate the Norton's current for the 15 volts, 20 volts and 25 volts. Now let's calculate Norton's resistance here. The next step is to find the Norton's resistance. To find out the Norton resistance, short circuit the voltage source and open circuit the load resistance. Okay, here from this to find Rn, as we know that these two resistors are connected in parallel. So R is equal to, the formula for parallel is R1 into R2 by R1 plus R2. Okay, we will get 0.9 kilo ohms. Now, these two resistors are converted into one single resistance by using the parallel operation. Now, if we take that value here, here 0.9 kilo ohms, that is connected in series with 1.8 kilo ohm. 1.8 kilo ohm, this is called as Rn. If you see the circuit here, 0.9 kilo ohm, that is connected in series with 1.8 kilo ohm. So R is equal to, we will get R1 plus R2. So finally Rn is equal to, we will get 2.7 kilo ohms. For the given circuit, Norton's resistance is 2.7 kilo ohms. This is a procedure. These two are connected in parallel. The turns are connected in series with 1.8 kilo ohm. Okay, so this is a 2.8 kilo ohm. We have to indicate in the tabular column. Next, to find out IL dash. Now let's find out IL dash for the IN is equal to 2.77 ohm. This is the current source, that is IN. IN is equal to 2.77. Okay, milliamps. 2.7 milliamps, that is connected in parallel with Rn. Rn value we got 2.7 kilo ohms. Here we have to find out IL dash in this branch. Okay, here to find out IL dash, here I am using current division rule. By using current division rule, the formula we will get is IL dash. The required current IL dash is equal to total current. What is the total current here? IN is a total current. Total current into opposite resistance of this RL is Rn divided by Rn plus RL. This is the formula we use to find out IL dash by using the current division rule. Here, IN value is 2.77 and Rn value we got 2.7 divided by 2.7 plus the RL value we have 1 kilo ohm. Okay, as all the resistors are in the kilo ohms, we will get the current is in milliamps. Okay, IL dash for the IN value is equal to 2.7. We will get 2.02 milliamps of IL dash we will get. Okay, now let's see for the remaining circuit here. IN is equal to 3.7 milliamps here. Okay, this is called as IN. The value of the IN is equal to 3.77. This is in milliamps. Okay, Rn value we got 2.7 kilo ohms. Here we have to find out IL dash. Here also same, we are using the current division rule to find out the IL dash. By using the current division rule, the total current is 3.77. Okay, or 3.7, whatever it is. 3.77 into total current into opposite resistance is 2.7 divided by 2.7 plus 1. If we calculate this, we will get 2.7 milliamps. IL dash is equal to 2.7 milliamps. 2.7 milliamps. Now let's see by taking the one more Norton's current here. IN is equal to 4.6 milliamps. Here Norton's current IN is equal to 4.62 milliamps for the Norton's current IN and Norton resistance RN. Here also we have to find out IL dash in this branch. The same current division rule we are using here. Total current is 4.62 into opposite resistance. The RN value here, it is here also it is RN value. Okay, RN value is equal to 2.7 kilo ohms. If we calculate the opposite resistance is 2.7 divided by 2.7 plus 1. If we calculate the IL dash value for the given IN, we will get 3.37 milliamps. We will get IL dash. Now see, whatever the parameters we got up to now, that if we summarize this is the given circuit. Okay, for this given circuit, this is the equivalent circuit here. This equivalent circuit consists of IN, Norton's current source, that is connected in parallel with RN. Okay, the current passing through this branch is IL, and the current passing through this branch in the equivalent circuit, we are assuming that IL dash. Okay, for the given circuit, this is the equivalent circuit. Okay, so if you see the whatever the values we got up to now, for the 15 volts and 20 volts and 25 volts, if we apply the supply voltage, IL value 2.02 we got, and in the equivalent circuit IL dash also we got 2.02. And for the 20 volts we got IL value is 2.7 milliamps and IL dash value also 2.7 milliamps. For the 25 volts, the IL value is 3.37 milliamps and the IL dash value is 3.7 milliamps. From this we can say that IL dash for the three different voltages is equal to IL dash for the three different currents IN. Okay, so from this we can say that hence the Norton's theorem is verified for the three different voltages 15, 20, 25. Now this is about the Norton's theorem verification for the theoretically verification of Norton's theorem. In the next class we will see how we will verify the Norton's theorem practically. Okay, thank you everyone.